This is our 24th lesson on the biblical flood, and we're dealing with the revised edition of my book, The Biblical Flood, and this will be the second edition of it. And I've decided to add another chapter to the book. Okay, there's some material that I have that doesn't really fit into this chapter. I've got it with it in my notes, but I'm not going to. I'm just going to add another chapter to the book. And we'll talk about it right at the end of the lesson today, just briefly, okay? Kind of let you get a feel for it, right? Let's look at, of course, I've taken the position that God providentially brought a planet close to the earth, that the planet approached the earth above the ecliptic plane. Now let's talk about what the ecliptic plane is. The ecliptic plane is an imaginary line from the center of the sun to the center of the earth, going out into space. That's what it is. And so my contention is that this planet, and I think it was the planet Mercury, and I've got several reasons for taking that position, that it was, and its orbit was outside the ecliptic plane. It was above the ecliptic plane. So it orbited like this. It went out and then went close to the sun and come back out. So it was very elliptical, but it was above the earth, above the ecliptic plane. And it then come down and it was nearly captured by the earth. That it encountered the earth in late summer, probably July or early August, late July, early August. Now the earth is in an orbit that's elliptical, egg-shaped, if you want to call it that, and it's different distances from the sun at different times of the year. Now, in the northern hemisphere, which is more land, more earth and land, than the southern hemisphere, which is more water, land surface warms up more quickly and cools off more quickly than water does. Water holds its temperature very well. It takes a lot of energy to heat water up in order to cool it off. And so water, the surface of water, the Lord put the earth in the orbit that it's in because it's best for us. Now, what we have is in July, we're the farthest from the sun that we can be, around the 4th of July, and the orbit of the Earth. That's called aphelion. It's from the Greek preposition apo and helios, or sun, aphelion, from the sun, apo. And then perihelion is when it's the closest to the sun. That's around the 9th or 10th of January. Now then you say, well, why is it so cold in the northern hemisphere in January? Because the Earth's tilted on its axis several degrees. Now you can see it's depicted as being tilted right here in the tilt. So the Earth is tilted. As it goes around the sun, in January it's tilted away from the Earth, from the sun, but we're closest to the sun. So we're tilted, and we're tilted toward the sun in July whenever we are the furthest from the sun. But again, this keeps the temperature of the northern and southern hemispheres more constant because the water takes a lot of energy to heat up and cool off. It's predominantly what we find in the southern hemisphere. But we won't get into that any further, but I will lay this out. My contention is that it came down across the earth like this. And here's the planet. I believe it had ice rings, perhaps other particles, rocks and so forth in those rings, but mostly ice. My contention is probably mostly ice. And that rings in it. So it circled the earth, I believe, 3 times. It's possible I'm wrong. It might be 4 times, but I think it was 3 times as it circled the earth. It circled the earth, and the sun, as it started, the earth began to get closer to the sun, then the sun's gravity had more effect upon it. Gravity is a function of distance, and it's the square of the distance, I believe, it's cube of the distance. So what we have here is gravity. Whenever we decrease the distance, we're going to increase the gravity. So as the Earth gets closer, then this planet has more, the sun has more influence on pulling it toward the sun. Right? Now, so it's above the ecliptic plane that comes in. Now we have the moon involved here in it as well. And I believe that it pelted the far side of the moon as it came in with some of its rings. So some of its rings, I believe, hit the far side of the moon, impacted their far side of the moon, the side. Now, again, if we take our ecliptic plane, we have a north as it comes in. It's a little larger view. It comes in above the ecliptic plane, and then it goes down like this. The first time it goes down like this, but the sun is tugging on it over here in this point. So the next time it circles, it goes down like this. It goes down a little less. Then the third time it comes down and it circles around, it gets up more closer to the ecliptic plane. And so circles back around, and as it swings back, it gets farther enough, close enough to the sun that the sun then pulls it away from the Earth. And that would take about we'll get our time here in just a little bit. Okay, any questions anyone has? Right, the Earth is tilted on its axis, keep that in mind, and the magnetic field is not lined up with the geographic poles. So that's another thing we need to explain it, and I believe we can explain it with our model. All right, now what we have here is, as it moves around the Earth, its gravitational field will affect the Earth. Now we're going to come back in just a moment. We're going to show some pictures of some things that have happened, and then we will explain them and come back with this model again to explain it. Right here, we have plates moving against each other in a collision, and when they do this, they have an upwelling of material. And so this is a claim that the collision, they squeeze together and deform, and we get metamorphic rocks, which are heat generated, and we get a mountain range elevated. And of course, they claim this happened this is in Iran, I believe. And this, I believe it's in Iran. They call it an orogen. Oros is the Greek word for mountain, and genesis is the beginning of something. So how mountain, one-way mountains were formed, right? This is a simulation of it with using colored sand, and they simulated it. And so they pushed them together. But I think they're probably right in this. And my model will actually explain this and show how it could perform, okay? Any questions? Now, this is in Iceland. This is two plates. I do believe there are plate tectonics, and my model will explain what is called plate tectonics, which they've battled around a while, but they've generally accepted as being real and that there are plates. This is the Eurasian plate and Laurentian plate, and they come together in the country of Iceland. This is a fault line where they go through, and it's a plate boundary, a fissure, they call it, on the plate boundary. Eurasian plate here in Iceland, this is Laurentian plate. So it looks kind of jagged, doesn't it, where they come together, right? Now, here's the problem with the Earth. If we take the Earth and we go back now, let's go back to this. When the planet comes around the Earth, they will exchange angular or spinning motion momentum. And let me illustrate this. We illustrated it earlier with an ice skater. The ice skater starts spinning, and then he has his arms out, and he pulls his arms in, he spins faster. And he conserves angular or rotational momentum. And that's what we have here. And when the planet comes close to the Earth, it interacts with the Earth through gravity and the tides it causes. There are actually three kinds of tides that occur. There is water tides in the oceans. Then there's land tides, which we're going to really get into here a little more tonight. And there's atmospheric tides. And so right now, the moon causes rotating systems of air movement. That's about 1/20th of a mile per hour. Now, it's not the moving weather systems we see. It's not caused by the moon. That's caused by something else. But what we have here is we do have rotating, and tides rotate. Okay. And so what we have is we have them rotating. And so there's 1/20th, and I'll document this later, 1/20th of a mile per hour tides in the atmosphere caused by the moon. Okay. We'll come back to that at a later time. So there's three kinds of tides. There's water tides in the oceans and even in the bathtub, but it's so small we can't measure it really, probably. I doubt that we have instruments sensitive enough to even measure it. We might have. They might develop some, but it wouldn't be very much. It wouldn't move very much. We also get it in the Great Lakes, and I think it's like an inch of tides a day, go up an inch or so in the Great Lakes in the United States. So a large body of water like that will have small tides. Mediterranean Sea has some smaller tides. But what we have here is there's tides in the water, there's tides in the air, atmospheric tides. Most people don't know that. And the third thing is there's tides they're called solid tides or land tides, where the land, the surface of the earth moves up and down. And this occurs, they can actually measure it. We talked about this last week, so we'll come back to it a little more. So when this planet now, when it goes near the earth, it interacts through the tidal function. The earth causes tides in the magma on the surface of this planet as well. So when it does, they both interact and they'll change their speed. So what happens is when it turns, it would slow the earth down and speed up the planet. Right now, the moon causes tides and it slows the earth down slightly and it speeds the moon up a little bit. And so it's constantly doing that. And that's in some pretty basic physics, okay? Now let's move on. Back to this. And this would create, and I will explain in just a minute how it would create movements in two different directions. All right. Again, we're going to have these fissures on the plate boundaries that will occur. Now then, if the Earth, let's go back now to this, if the Earth slows down in its motion due to exchange of angular momentum, rotational momentum, if it slows the Earth down, then the Earth, as it's been slower, and this would be pretty significant change in the angular momentum, but by a large planet coming near the Earth, and the things that would cause the flood. So it would change the Earth's shape. The spinning motion of the Earth causes it to bulge at the equator. So the equator bulges. If we slowed the Earth's rotation down, that bulge would have to depress. It wouldn't go out as far, and something would have to happen. So here's what would basically happen. We'd see something like this right here. It's like you take a piece of carpet or a rug, and you can ripple it up if you move it. And so right here, the surface of the Earth could ripple, and this could happen. This is one of the things they believe happens in the surface of the Earth, so it elevates parts of the Earth. All right. Now we again approach the planet above the ecliptic. Now keep that in mind. It approaches, comes down, and then it goes through like this. Okay, let's move on. According to Tomasek's measurement in Marburg, we've had this last week, the M2 land tide has an amplitude, that's the height, of roughly 0.5 meters. Now, 1 meter is 39.37 inches. So it's around 20 inches, approximately, in the ballpark figure. that is the Earth's surface, rises and falls twice daily about 0.5 meter, about 20 inches. Naturally, this rise is imperceptible as there is no fixed point from which to measure the fluctuation, since the observer stands on the Earth undergoes the same motion. So an observer that's going to observe it, he would rise with it, and he wouldn't see any motion but it is there, and it can be measured with satellites and other things. So right here we see there is a land tide. This is land tide. And we also, it's called solid tide. Smith discusses this, and under the phenomenon he calls solid tides, but it's the same thing. He says instruments capable of measuring small changes in local gravity or small tilts in the Earth's crust indicate that the solid Earth is also subject to tides, implying the Earth does not respond as a rigid body to a gravitational attraction of the sun and moon. Now, most of our tides come from the sun and moon. Now, we do, if Jupiter gets in the right position, it causes a little bit of tide. It's not real large, but it's a pretty big planet, so it does cause some tides. Defunct, right here, Smith goes on and says, typically an observer on the Earth's surface will move up and down in 12 hours by as much as 500 millimeters. Well, that's half a meter. And that's what we had with the other source, about 20 inches. I added that into the quote. At the same time, gravity on the surface will change fractionally. This is the solid or elastic tide. The amplitude is a function not only the magnitude of the tide raising force, but also the elastic properties of the Earth. Now, if you provide enough force on the rocks, it'll break the rocks apart. Now, that's what happens. So if we had solid rocks and they had tremendous force applied to them, it would fracture the rocks. They would break apart. So it's somewhat elastic, but it'll bend a little bit, but not much. Solid rocks will. Gravitational forces are inversely proportional to the cube of the distance. That's Wilson Pascoff. This is a university level general physics book. Now, if we take this basic formula for gravitational forces, if the moon were to come within 15,000 miles of the Earth, now it's about roughly 250,000 miles from the Earth in round terms right now. I think 245 or something like that, 1,000 miles, roughly 250,000 miles. If the moon came to within 15,000 miles of the Earth, its tidal force would be about 4,096 times what it is now. That would be the tidal forces. Now, if the present gravity of the moon causes the surface of the Earth to rise 0.5 meters, about 20 inches, and the force will increase over 4,000 times, the surface of the Earth would rise about 2,000 meters. So we take 0.5 times 2,000. That would be about 6,560 feet. That's a pretty significant rise just from the moon being 15,000 miles from the Earth. So kind of keep that in mind. And you get 15,000 miles, and we'd use the formula for gravity. So that's, if we take a planet the size of Mercury, and that's what I'm convinced caused the flood, if it came within 15,000 miles of the Earth, then it had a mass of Mercury's mass. It would raise the surface of the Earth by over 9,000 meters, about 30,000 feet, approximately. And that would explain nearly all of your mountain ranges right there, and it would elevate them up. Now, another thing that would explain them, it would explain some of your mountains, not all of them. Some of them are volcanic, and some of them are caused by the change of the Earth's rotational circumference at the equator. And I believe the Andes Mountains were formed by when the Earth slowed down its rotational speed, and then it had the equator then had to elevate itself because it was too long around the equator, so it had to take the slack up, and that would be kind of like these right here. Go back to them. It would be much like this right here. And so if you stretch this out, let me use and stretch this out this way and this way, these humps would go down. It'd be like a carpet, rug, a rug that's movable, not nailed to the floor, and it could ripple up like this. You probably have seen that occur. So if we stretched it out and made this circumference of the Earth bigger, then this would be the surface of the Earth to be level. But if we shrink the diameter, the circumference of the Earth, make it smaller, then we got to take the material and something has to happen to it. And I believe that's what caused the Andes Mountains. That's my mind, that's what caused them. I realize that people are going to say, well, who's Marion Fox? But it doesn't matter who I am. What we have to ask is these things, does my model explain these things? That's all that's important. Now let's look at, if we take strata of rock, and if our strata is laid down, now I'm addressing this to those who believe in the flood. If we have the rock laid down in layers, it would be strata that's parallel to the surface of the Earth, like I'm doing my mouse. But if we elevate it with a force centered up here somewhere, that force pulling it upward, then that strata would be elevated up here. It'd be tilted like this. And so if a flood occurred after the sediment was layered, layers of sediment occurred, we'd have the mountains like this if the mountains were raised after this. Now we don't see that entirely. We see some strata like this, and we see other strata like this. This is kind of a simplified view, but I drew this. And so we have our strata in different layers. So as the planet circled the Earth and the Earth rotated on its axis, we would get various strata laid as the tides went in and out from the tidal flood. So we'd have various strata, and some would be elevated up, some would be like this. This is what we actually see on our mountains, some of our mountains. Now, the moon, let's look at the moon. The moon, we would normally think that the moon would be in the ecliptic plane. Let me see here, I think. Let's go back. I'll go back to the ecliptic plane again. And I realize I'm jumping around a bit. But if we take the ecliptic plane, an imaginary line to the center of the sun, center of the Earth, ideally, if this thing occurred billions of years ago, the moon should be pulled down into the ecliptic plane. When it comes out here, the sun should have a vector force on it, pulling it upward slightly. And so it would pull it upward, and then the Earth acting upon it as well. So it should be in the ecliptic plane after billions of years, but it's not. It's above the ecliptic plane. I think it was probably in the ecliptic plane when the Earth was created. But I believe that what we see here is possible that when this happened, what happened is the planet being above the moon, some of its rings hit the far side of the moon, and it tilted, pulled the Earth up above the ecliptic plane. It's inclined. It's about 5 degrees above the ecliptic plane. So this is not drawn to scale. So the ecliptic plane is out here, and about 5 degrees up is the moon, which goes down over here about 5 degrees down. It's a little bit different value up and down, but it's about roughly 5 degrees on average. Okay. So now what we have is we actually have 2 tides from the moon. We have one on this side and one on the other side. You might think of it this way. It's not the force, it's the differences in force. Now let me talk about how a tide occurs. This force, if we take the center of the moon and just project it down, there's a force right here. The force will be the biggest the closer it is. So if it's aimed at this part of the Earth right here, and it's right perpendicular to it, let's just say it is, then the force will be biggest right there. If we get further away over here, the force goes down with the cube of the distance. So the forces of the tide get smaller as we go around. Let's go back now, I hit it with the mouse. and it would get smaller as you go down this way. So again, what we have is the tidal forces are the tides occur because of differences in forces, the forces being different. If the Earth were a bowl shaped like this, then there would be no tides if it were bowl shaped, which it's not, of course, because the distance would be the same on the water if it were a bowl, but it's not, of course. So we do have tides moving, and we get the tides in the land for the same reason and in the atmosphere for the same reason. But what we see over here is we're also pulling, you can think of pulling the Earth away from the water and the atmosphere over here. And again, the differences in distances, this is closer to this point than it is to this point over here. So again, we have a difference in distances, and the difference in distances is what causes the tide. So we get a tide on both sides of the Earth. We have a high tide here and a high tide on the other side of the Earth at the same time. Are there questions about this? All right. Some instances depend on where the Earth is, but we get one tide a day, and then we get two tides most of the time. Diurnal. 2 tides a day. Okay. And we're not going to go any further into tides. They're a little bit complicated. All right. Now, right here, the tidal forces, these are differential. They're changes. They're different. And so the tidal forces, let's say your satellite, and let's say this is the moon. The forces are greater here. And notice they're directed at the center of the moon over here, the center of the satellite. So they're not straight out, like this one's straight out perpendicular, but this one goes tilted a little bit. So these tidal forces are tilted. So if we take the crust of the Earth that's also being pulled, then this crust over here is being pulled in that direction, but this crust is being pulled in this direction. They're not parallel in forces. And so the forces up here are this way, whereas down here they're this way. So pieces of the crust would be influenced and pulled in different directions. So the crust of the Earth, and this is what we're talking about with the plates, the various plates would be pulled in different directions. Any questions or comments there? Anybody? So this pretty satisfactorily, pretty easily explains the difference in the motion of the plates. The plate that was attached to this right here would move this way. The plate that's attached right here would move in this direction. This plate here would move this way. This plate over here would be moving the other direction. So they would be moving, and as the satellite moved, it would move the plates as it went around in different directions. And so it would take the force of a plate that was maybe fractured apart when the Earth changed its rotational circumference because it slowed down. When that happened and we fractured the crust of the Earth, each of these plates are going to have various forces. At any instant, it may have a force this way at some instant, and then later when the satellite moves around further, it may make it move this way. And so it would be the vector sum of all those forces together. We'd have to add them up. It'd be way too complicated to even try to figure it out. But it could move it this way for a while and then turn around as the planet moved. Could maybe move it this way, and then a force moving it this way. And then when it moved away, it would still be moving maybe in this direction. So the plates would move in different directions as they do. We'll see this in just a moment. Here's your geologic provinces, and we won't go into this any further, but this is the geology of the Earth and the various kinds of things they have. We won't go that in any further. I won't spend more time on that, but that's kind of what it looks like. Here's the Andes Mountains, and as I say, I think the circumference of the Earth got smaller at the equator because the Earth slowed down in its rotational speed because it gave up angular momentum. So what happened then is the oceanic crust from the west side moved under the crust that was there on the west side of South America. And this elevated the Andes Mountains up a ways from it, including causing volcanoes. And so that's my contention. That's a simple explanation for it. And all these forces had to be expended. these pieces of crust of the Earth, the plates, are massive in mass. And what we have is, it's like a car. You start it rolling, a big heavy truck or something, and it takes a lot of force to stop it. Well, these masses are way, way beyond what you get for a car or even a train. And so what we have is we have massive mass, a tremendous mass. Once it started moving, then it's real hard. It takes probably thousands of years for it to slow down very much. So it's going to continue to move. And so that's why these plates do move. So I think the Alps also function this way as well, the crust movement in two different directions. But in this case, we have the crust moving this way. Let me go back, I'm sorry. We have the crust moving this way and the crust moving this way. So these two, as we have it here, they move in opposite directions. So our mountain ranges occur, and I think that's probably your Alps will function that way as well. Okay. Here's a picture of some right here. The previous slide is an example of thin skin deformation according to the geologist, thrust faulting, and that's what we're talking about, is thrust faulting. This is thrust faulting right here, okay? They claim this is an example of it. It's real hard to see it, but they're claiming that this is an example of that, right? Let's go much more further. This is in Montana, and we have white Madison limestone repeated with one example in the foreground that pinches off with distance. Another in the upper right corner in the top of the picture. So let's go back and look at upper right corner in the top of the picture. I've thought these were snow, but I think they're what he's talking about here is this is not snow, is what I think. I think we're seeing it there. Maybe over here, it may not even be snow there, but I've always thought that was snow, but I think that may be what they're talking about. But this is how it was explained. I picked this up off a website. Here's some of the white stone we have here as well. All right. It's claiming it pinches off. So it might be that they're looking at this right here, pinches off right in here. Okay. Here are your plates. This was plate tectonics. And what we have is we have the Eurasian plate, which is over here. And then it goes out, and here's the Caribbean plate. And here's the South American plate, Scotia plate, Antarctic plate, Pacific plate, Australian plate. And the North American plate goes over and takes part of Russia, doesn't it? So here, notice here, the plate here, North American plate, goes right through the center of Iceland. And that's what we saw earlier, right in through here. So with the Eurasian plate and Laurentian or North American plate is called. Right. So these plates all move in different directions. They're tended to move. And right here, we have right in here in California, these plates are moving in opposite directions. And again, this could happen easily if the planet is in a different position and it has vector forces pulling them in different directions. And if we go back now, let's go back and look at these vector forces, let you see what I'm talking about here. The forces, if the satellite is over here, it'll be straight here, perpendicular, and these other ones will be at angles. And some of them will move this way, some will move this way, some will even move right perpendicular to it, some will move opposite to it, as this is pulled away from the other. So the forces, believe it or not, will be opposite directions on the other side. And so again, all of those together will add together and give you the force on these plates. The plates then would be expected to move in opposite directions. Okay, it's not surprising that they would with this model. Are there questions or comments?
Yes, Brother Larry, and I do have one for the Williams. With the slide you just showed us with the differential tidal forces, the forces go. I see they go inside, north, and south. So, are they building up pressure to more pressure when they move outside, like to the east and west? I see the arrows pointing outside.
Well, the arrows here will probably be the strongest, and I think they get weaker here, but they just go in different directions because they're going toward the center of the, and it's the difference in the forces is what it is. It causes the tidal actions and causes, in this case, it is a force moving pieces of rock, moving chunks of the plates over there, sections of the earth, pulling on the earth. You got fantastic forces. If you had a planet the size of Mercury, it's 15 or 20,000 miles from the earth, it would raise mountains up right easily. I don't know if I'm answering your question, but these forces all go in different directions, and they won't be actually the same magnitude either. They'll be different directions and different values of force magnitudes.
Okay. Yeah, that answered it. Thank you.
Now, right here is another one. This is from another website that I picked up. It's from a NASA website. These are the directions of the forces, the movement of these plates, which fits in with my model to a great extent. So it depends on where all of this motion could have been occurred whenever the planet was over here pulling it real strongly. Right over here is a lot of forces across the North American continent, tremendous forces. But notice, which way is Australia moving down here? It's moving generally up to the northeast in that direction. Hawaii is moving that way. Look over here. All right. It's moving this way. So again, these plates are moving in different directions. That's Auckland, New Zealand, probably. It's moving this way. And again, these are at angles. Notice they're at different angles. And again, this goes back and fits in with the model we had here. Let's go back. They're at different angles here, if you notice. See them? That's exactly what we expect with satellite. They'll move in different angles.
Yeah, I noticed. Okay. Thank you.
All right. Any other comments? Questions? All right. They claim the Himalaya mountains were formed when an island or a piece of subcontinent actually moved up. And they give these times, and that it ran into or moved up into the Eurasian plate, and then elevated the Himalaya mountains up here. That's what they claim. That's possible. It could have happened if this slid across the surface of the Earth and moved upward. But I don't think it took this large amount of time, because the flood model could have done it in a few months. And so again, the time frame is, I would disagree, but it's possible that it was formed this way. All right. Here's something I was going to study this a little more, but it's a Aurelian plate in the Rocky Mountains. They claim that there's an upwelling of stuff underneath that caused it, but too much information on it. So I'm just going to let it go. We have sandstone, conglomerate, and rocks, which are composed of large objects, give evidence of having been laid by turbulent waters. Now, these are rocks that indicate the water was very turbulent, that it was moving quite a lot. And we don't have just easy currents of water. It has to be pretty strong currents to do this, to form these kind of rocks. Shale and other rocks are composed of fine-grained materials such as silt. It takes water that's very slow moving for the silt to settle to the bottom. And so that shale would be rocks that are where the water is not moving very much. Well, at different parts of the Earth, at different times, as the planet rotated around the Earth, moving around, cycling through, particularly when it got far away from the Earth for a few days, then it came back. And during that time, it could lay shale and other rocks, such as silt, that would be laying something the water would be settled down, not move very much, and it could settle. And times when the water is moving quite viciously, quite actively, then very turbulent waters, it could have sandstone or conglomerate or other rocks. So again, this will explain the different kinds of rocks at different times. The model will do that. I'm convinced it was Mercury, and we'll give other evidence later for it. When it was close to the Earth would rotate on its axis. One side would experience considerable turbulence. At the same time, other parts of the Earth would experience quiescent or very quiet conditions. Again, we could be laying one kind of rock in one part of the Earth, and at the same time laying other kinds of rock, shale and so forth, at other parts of the Earth. The side experiencing turbulence would have sandstone conglomerate, where large chunks of rock and things are put together, being laid. The side that's quiescent condition would lay shale for us. Shale is almost for certain laid by waters that are quiet. They're not moving very much, they're pretty still. It explains that while there are various layers of rock, shale, sandstone, conglomerate, and even various fossils in both kinds of rocks, same fossils. Didn't require millions of years because the flood model developed will explain these changing conditions in a matter of days rather than in years, or thousands or millions of years. Now then, are there questions? Anyone got questions? I'm going to introduce another thought with a couple of things here, and I want you to be aware of this. We have what are called Fluval Lakes, and I'll give a quick synopsis of it. Find it. Landlocked lakes, they're called Fluval or Paleo Lakes, and I believe that they were caused by the flood. And we'll be looking at some of those, and I'll develop a chapter on it. And these were full of immediately after the flood. After a few centuries, the climate became more and more arid or dry. The lakes dried up. Lake Bonneville in Utah primarily is an example of this. And there was a layer of salt at Lake Bonneville. And the lake bed was unfit for agriculture. Here's some of these lakes, and they're all over the western part of the United States. We see them in other parts of the world as well. But here's Lake Bonneville, and here's Lake Hunton. But there were other lakes that have been documented and shown to exist. I'm claiming that these lakes were there as a result of the flood, and that they then drained out and evaporated, and the climate, of course, changed at that point. So we have changes in climate due to these lakes drying up. Now, we'll come back to this later, but I'm going to write a whole chapter on it, so there'll be a new chapter on this. But there's also another kind of lake. These are lakes caused by ice or melting ice. So I believe there was ice here, and we'll get to the Fluval Lakes. There are other lakes, and we'll come back to these later, but we have lakes glaciers. So we'll come back to those at a later time, okay? So we have glacial lakes, and some of them were quite large, and we'll see some effects of them, okay? And Fluval Lakes, and we'll be looking at them. All right, are there any questions? Okay, what we're going to do is we're going to stop the recording.